In this video, we will be talking about arc length and curvature. We define the length of a parametric curve in two dimensions as L equals this definite integral, provided that the various functions and parameters are all well behaved. The length in three dimensions is defined similarly. Suppose r of t is equal to the vector composed of f of t, g of t, and h of t on the interval from a to b, where f prime, g prime, and h prime are continuous. If the curve is traveled exactly once as t increases from a to b, then we have that the length is equal to this definite integral. Notice that we can also write the length is equal to the definite integral from a to b of the magnitude of the derivative our position vector with respect to t. Example 1 says a glider is soaring upward along the helix r of t equals 3 sine of t plus 3 cosine of t plus 4t. How long is the glider's path from t equals 0 to t equals 2 pi? So let's just really quickly visualize what is happening here. So if I evaluate r of 0, that's going to give me 3 sine of 0, 3 cosine of 0, and 4 times 0. And this is going to equal 0, 3, 0. So if I were to visualize this, that would be my starting point. Here's 3, 0, 0. So our glider is starting there at time or t equals 0. We've explored this kind of previously, but because the sine function is in the x component and the cosine function is in the y component, that means that we're going to travel clockwise instead of counterclockwise. And notice that as the t value increases, the z component or the height is only going to increase. So it's going to end up looking something like that until it travels kind of back around and then ends up with the same x and y coordinates, because if we evaluate r of 2 pi, that's going to equal 3 times sine of 2 pi, 3 times cosine of 2 pi, and then 4 times 2 pi. So again, just to reiterate, the x and the y component of this vector will be the same as r of 0, and then now the height or the z component will be 8 pi. So let's say that ends right there. And what we're doing is we're trying to figure out what is the length of the glider's path from t equals 0 to t equals 2 pi. All right, so I've just kind of rewritten the arc length formula here. So in order for us to use this formula, we need to find the derivative of r. If we do that, we end up getting 3 cosine of t, negative 3 sine of t, and then 4. And now what we'd like to do is we'd like to take the magnitude of this vector. So that's going to equal, if I square each of the components, that's going to be 9 cosine squared t plus 9 sine squared t plus 16. Notice that we could factor out a 9 from the first two terms. That will give us the Pythagorean identity, and cosine squared plus sine squared is equal to 1. So that's going to be the square root of 9 plus 16, which ends up equaling 5. Okay. So filling in our integral details, we have the limits being from 0 to 2 pi, and we found that the magnitude was equal to 5, and then we are taking the integral with respect to t. So this is going to equal 5t, evaluated from t equals 0 to t equals 2 pi. And then if we plug in these limits of integration, we should get 5 times 2 pi minus 0, and that ends up equaling 10 pi units. So that is the length that the glider traveled, the length of their distance traveled. So just as a reminder, the length of a curve is a constant or just a number. The arc length is similar, but a function. So those are defined there in this purple box. One is a constant and one is a function. Let's move on to talking about curvature. A parametrization R of t is called smooth on an interval I if R prime of t is continuous and non-zero on I. A curve is called smooth if it has a smooth parametrization. A smooth curve has no sharp corners or cusps. When the tangent vector turns, it does so continuously. If C is a smooth curve defined by the vector function R of t, recall that the unit tangent vector capital T of t is given by the function capital T of t is equal to R prime over the magnitude of R prime and indicates the direction of the curve. In the picture, you can see that capital T of t changes directions very slowly when C is fairly straight, but it changes direction more quickly when C bends or twists sharply. So here you can see that the tangent vector or the unit tangent vector is not changing direction that quickly, but when it curves, notice that the direction of the unit tangent vector does change quickly when it curves. The curvature, this is a Greek letter called kappa. At a given point is a measure of how quickly the curve changes direction at a point. So one way that we can define curvature is it to be the magnitude of the derivative of the unit tangent vector with respect to the arc length of the curve. While possible, it is a nuisance to find capital T as a function of S, but notice that with the chain rule, we can rewrite the derivative like this, and from this rewritten chain rule, we can solve for dt ds by dividing both sides by ds dt. And when we do so, we get this second definition. So here we have this in the numerator and then this in the denominator, and so we can rewrite that as the curvature is equal to the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector. So this is a second definition for curvature. Example 2 says find the curvature of a circle with radius a centered at the origin on the xy plane. So let's draw this. Here's my y-axis, here's my x-axis, and I have this circle here. And we know that it has a radius of a, so then this will be a comma 0, this will be 0 comma negative a, and so on. Okay. And we would like to find the curvature. So one thing that we can do is we can parametrize our circle. And if you don't remember this, let's give ourselves a reminder. So if you don't remember from when we talked about parametric equations, a circle centered at the ordered pair h comma k with radius r, we can parametrize that circle and let x equal h plus r cosine t and y equal k plus r sine t. So we want to use those parametrizations to come up with our vector valued function, r of t. And here, because we are centered at the origin, that means h and k are going to be 0. And r, our radius in this case, is going to be a. So putting all of that together, our vector valued function will be a cosine of t and a sine of t. All right, so from here, what do we want to do? Well, I would like to find the curvature, and I'd like to use this definition. So from here, it would be helpful to find the derivative. So let's do that. I'd like to find r prime. That is going to be negative a times sine of t, and then a times cosine of t. As a next step, I would like to take the magnitude of that vector. Doing so will give us a sine squared t plus a cosine squared t. And we can factor out a squared from both of those terms, if I remember to put the squared. Now we can factor out a squared from both of those terms, and we'd be left with the Pythagorean identity, which is equal to 1. So that's going to be the square root of a squared, and that's going to give us a in this case. From here, what I'd like to do is I'd like to put this information together to create the unit tangent vector. And we know from earlier that that's equal to r prime over the magnitude of r prime. And our r prime vector was negative a sine of t and a cosine of t. If I divide that by our scalar magnitude a, notice that both of our components in our r prime vector are being multiplied by a, so I can divide each of those components by a, and that will leave me with negative sine of t and cosine of t. All right, from here, going back to the curvature definition, I'm going to need the derivative of the unit tangent vector. So now I'd like to find capital T prime. If we do that, that's going to be negative cosine of t and negative sine of t. Then, as a next step, we'd like to find the magnitude of t prime. And if we do that, that gives us cosine squared t plus sine squared t. Again, using the Pythagorean identity, that's going to be the square root of 1, which is equal to 1. Let's put all of these pieces together now. So our last step, our curvature function kappa, or kappa of t, because it's a function of t. Remember, curvature is going to depend on how much time passes and where you're at on the curve, so it's a function of t. And it's equal to the magnitude of t prime over the magnitude of r prime. And the magnitude of t prime we found in the previous step was 1, and then the magnitude of r prime we found previously was a. So when it asks for the curvature of a circle with radius a centered at the origin, something that you'll notice is this thing here is a constant. So this is our curvature, and it is constant. So that's kind of interesting. Remember, a represents the radius of our circle. So let's run through a quick example. Suppose I have a circle centered at the origin that had a radius of 3. So let's say this was 3, 0. Then for this circle, at every point on the circle, the curvature would equal 1 over 3 because the radius is 3. So here's another observation we can make. As the radius of our circle gets bigger, the curvature gets smaller. They have this reciprocal relationship. So if I had another circle whose radius was 100, then if I were calculating the curvature at any point on the circle, the curvature would be 1 over 100. Let's kind of walk through why this should make sense. I love to explain the idea of curvature as, suppose you are in a car and you're driving along the path of your curve. So let's say in this instance, I'm right there. Let me use a different color. So let's say I'm right here and I'm traveling along in my car the path of my curve. In this case, it's a circle. So when you're driving, I like to think of curvature as a measure of how much are you turning your steering wheel. And so one thing that you can think of is if you're driving along a circular path and you keep driving along that circular path, you're not changing the position of your hands on the steering wheel, and you're not changing how much rotation you're doing on the steering wheel and once you get on that circular path. So that is why our curvature for these circles is a constant, because it's a measure of how much I am turning my steering wheel. Another thing that you'll notice is as you compare these two circles, we talked about them having a reciprocal relationship between the curvature and the radius. And if you've ever driven in a roundabout, a circular roundabout, you will notice that if the roundabout is larger, you don't have to turn your steering wheel as much to get around this circular path, as if you were driving in a smaller roundabout, you have to turn your steering wheel more because it has more curvature. Here's just a quick illustration. Here is what a roundabout looks like when you're driving your car in one. And again, I just wanted to use this when you have a smaller roundabout or a smaller radius that leads to a larger curvature because you have to turn the steering wheel in your car more than if you were driving in a larger roundabout that has a smaller curvature because you are not turning your steering wheel as much. So again, they have this reciprocal relationship. Although the previous formulas work fine for finding the curvature, the following formula is more convenient to apply. So the curvature, again, which is a function of time, or a parameter t, is equal to the magnitude of the cross product between the derivative of r and the second derivative of r divided by the magnitude of r prime, and then taking that magnitude and cubing it. Note, this formula is not intuitive, and its derivation requires using the product rule, the fact that t cross t is equal to the 0 vector, and knowing that the magnitude of the unit tangent vector equaling 1 implies that t dot t prime equals 0. The full derivation is available in the textbook. Example 3 says find the curvature of a straight line parametrized by the vector valued function r of t equals c plus t times vector v. Let's start by taking the derivative of r. So we have r prime of t is equal to, this is a constant vector, so its derivative is going to be 0. And then we have plus t times vector v, and so that will give us that our derivative is vector v. And I just want to point out that this is a constant vector where each of its components is a constant. And then, so this was our first step. Our second step, we can find the second derivative of this, and that is going to be the 0 vector. Then as a third step, we have that our curvature function is equal to the magnitude of r prime of t cross r double prime of t over the magnitude of r prime of t quantity cubed. And this is equal to the magnitude of v cross the 0 vector over the magnitude of vector v cubed. And then this is equal to 0 over something that's not 0. And so 0 over something that's not 0 is 0. And we actually should have expected that to be the case before we even finished our calculation, because again, if this is a straight line, so here's my straight line, and my car is driving along that path, then our curvature is 0, because if I'm driving along a straight line, I am not turning my steering wheel at all. So that is the curvature of a straight line. Example 4 says find the curvature of r of t equals t squared, comma 2t plus 1, comma e to the t at the point 0, 1, 1. Let's start off by finding our r prime of t. We have 2t, 2, and e to the t. Then I am going to find r double prime. That's going to be 2, 0, e to the t. And now that we've taken both derivatives, we can plug in our specific value of t. So we want to find the curvature at this ordered triple. And you'll notice that if I set the vector t squared 2t plus 1 and e to the t, if this is equal to the vector 0, 1, 1, this implies that the only way that that would happen is if t was equal to 0. So now that I have that information, because I've taken the derivatives, I can plug in my t value of 0 into these. So let's do that. I'm going to find r prime of 0. That is equal to 2 times 0, 2, and e to the 0. That's going to become 0, 2, 1. I'm going to evaluate r double prime of 0. And we get these. So now what I'd like to do is, if you look back at the definition for curvature, we want to take the cross product of r prime of 0 and r double prime of 0. And for the sake of time, I'll just show you, if you take the cross product of these two vectors, you get 2, 2, negative 4. And then for our denominator, oh no, excuse me, I still need to take the magnitude of this. So and that is going to be the square root of 24. If we simplify that, that is 2 root 6. Okay, now we want to find the magnitude of r prime of 0 for the denominator. So that's equal to the magnitude of 0 to 1, which if you simplify that ends up being the square root of 5. And then step 8, I would like to cube that magnitude. So r prime of 0 quantity cubed is equal to 5 times the square root of 5. All right, now let's put all of this together to evaluate kappa of 0, which is the curvature at time t equals 0, or at the ordered triple 0, 1, 1. And this is equal to the magnitude of r prime of 0 cross r double prime of 0 over the magnitude of r prime of 0 quantity cubed. And we've calculated those things. That gave us 2 times the square root of 6 divided by 5 times the square root of 5. And if you threw this into your calculator, this is approximately 0.44. So remember, the larger the value of kappa or the curvature means that you are turning your steering wheel more, and then the smaller the value, it means that you're turning your steering wheel less. If your value is 0, that means that you're not turning your steering wheel at all, and there is no curvature. In this next subsection, we're going to introduce the normal and binormal vectors. But first, at a given point on a smooth curve r of t, there are many vectors that are orthogonal to the unit tangent vector capital T of t. We'll show that capital T prime is one of them. All right, so our goal is to show that these two vectors are perpendicular or orthogonal. What I'm going to do as a first step is I'm going to take the dot product between capital T and itself, which that's the same thing as the magnitude of capital T squared. And since capital T is a unit vector, this is equal to 1 squared, or just 1. Now what I'd like to do is I'd like to take the derivative of both sides of this equation with respect to t. So I'm going to take the derivative with respect to t of this and of this. So let's do that. I get the derivative with respect to t of 1 is equal to the derivative with respect to t of t taking the dot product with itself. And if we do that, the derivative of 1 is 0, since that's a constant. And then on the right-hand side, we're essentially using the product rule. We've learned a theorem that tells us that we're essentially applying the product rule. So it's the first times the derivative of the second plus the second times the derivative of the first. And I forgot the derivative notation here, so there. Okay, so these are like terms, and that gives me 2 t dot t prime. And then from here, I can divide both sides of my equation by 2, and that will tell me that, and I'm going to throw back in the input variable, is equal to 0. And we know from the dot product theorem that we learned in a previous section, therefore t and t prime are orthogonal. Since t prime is not generally a unit vector, we will define the principal unit normal vector capital N of t, or simply the unit normal, as capital N of t is equal to capital T prime over the magnitude of capital T prime. Note that capital T gives the direction of motion, and capital N points in the direction the curve is turning. The vector capital B of t is equal to capital T cross capital N. This is called the binormal vector and is perpendicular to both capital T and capital N, or the unit tangent and the unit normal vectors. The plane determined by the normal and binormal vectors n and b at a point P on a curve C is called the normal plane. And we can see a picture of that thing right here. So that one that connects, or excuse me, the normal plane is the one that has the normal and the binormal vector on it. So that here again is the normal plane, that one right there. It consists of all lines that are orthogonal to the tangent vector capital T. The plane determined by the vectors t and n is called the osculating plane. So the osculating plane is this one right here of C at P. The name comes from the Latin osculum, meaning kiss. It is the plane that comes closest to containing the part of the curve near P. Note, for a plane curve, the osculating plane is simply the plane that contains the curve. So in this first image here, we just have an illustration showing the right-hand rule, and this is going to represent the unit tangent. This is the unit normal, and then this is our binormal vector, and they are orthogonal to each other. And so here in this image, in this next image, this would be our tangent vector, this green one would be our normal vector, and then this would be our binormal vector. And you can see that again in the next image, which also shows the planes that are created by these three vectors and their names. The circle that lies in the osculating plane of C at P has the same tangent as C at P, lies on the concave side of C towards which n points, and has a radius. This variable or Greek letter here is called rho. And that represents the radius of our osculating circle, and it's equal to 1 divided by the curvature. Now, where is this equation coming from? We can see it again here, that the radius of our osculating circle is equal to 1 divided by the curvature. Well, in an earlier example, when we found the curvature of a circle, a curvature of a circle with radius a was equal to 1 over a, and so if you solve this for a, then you get a is equal to 1 divided by the curvature, but remember a just represented our radius, and so really the radius of our circle is equal to 1 divided by the curvature. So that's where this formula is coming from. So The osculating circle of C at P is the circle that best describes how C behaves near P. It shares the same tangent, so I just want to highlight, here's our osculating circle, and at our curve, the circle and our curve share this point P, and they share the same tangent line as well, and they share the same normal vector as well, and they have the same curvature at this point P. So here's a non-technical description. Imagine a car moving along a curved road on a vast plain. Suddenly at one point along the road, the steering wheel locks in its present position. Thereafter, the car moves in a circle that kisses the road at the point of locking. The curvature of the circle is equal to that of the road at that point. That circle is the osculating circle of the road curve at that point. So what is that saying? Let's use this picture here. So suppose you have a car here and you're moving along the path of our curve, so that represents the road. But let's say right as you hit P, let's say that your steering wheel gets locked. And so the curvature at that point is the same curvature of this circle. And so if your steering wheel locks and you can't change the direction or rotation of your steering wheel, then it would travel here, because then your curvature would stay the same at that point P. And so it would just keep traveling in this circle like that. That's what that is saying in the non-technical description. Example 5 says, consider the space curve r of t equals 3 sine of t plus 3 cosine of t plus 4t from earlier. Find the following things. So let's start with part A. It asks us to find the unit normal vector. So as a first step, I'm going to find r prime, which we did that earlier. That was 3 cosine of t, negative 3 sine of t, and 4. And then I'd like to find the magnitude of that. We did that earlier as well, so I'm just going to repeat from earlier. That was equal to 5. From our next step, we want to calculate our unit tangent vector. So we have r prime of t over the magnitude of r prime. So that's going to be 1/5 times the vector 3 cosine t, negative 3 sine t, and 4. Okay, so I just wanted to remind us the formula for the unit normal. It's equal to the derivative of capital T divided by the magnitude of t prime. So we found capital T, our unit tangent vector. Let's go ahead and find capital T prime. So from there, if I can use the constant multiple rule for derivatives, so I can just leave 1/5 and then take the derivative of each of the components. That will be negative 3 times sine of t, negative 3 cosine of t, and then the derivative of 4 is 0. Now I'd like to find the magnitude of this, so that is equal to, I can just take the magnitude of the vector and then multiply it by a scalar factor of 1/5. So let's see, if I square each of the components, I get 9 sine squared t plus 9 cosine squared t plus 0 squared. And if we use the Pythagorean identity, that's going to give us 9, or the square root of 9 rather. And then if I multiply that by 1/5, that will give me 3/5. All right, so let's put this together. Our unit normal is going to equal our t, capital T prime. So that was 1/5, negative 3 sine of t, negative 3 cosine of t, 0. And then we're dividing by the magnitude of t prime. which is 3/5. So that's the same thing as if I multiplied by the reciprocal. And so these will divide out, and note that that gives me 1/3, and so I can divide each component by 3. That will leave me with negative sine of t, negative cosine of t, and 0. So there is our unit normal vector. Let's go ahead and clean up the screen so we can do the remaining parts. It's going to be a lot of work, so keep some space on your paper. Part B asks us to find the binormal vector at 0, 3, 0, and 0, 3, 0, we get this when t is equal to 0. So we are trying to find the binormal vector when t is equal to 0, and according to our formula from before, this is equal to the cross product of t and n. But now specifically it's going to be t of 0 cross n of 0. We had our capital T vector earlier, but I erased it, so I'm just going to tell you when we plug it into, or when we plug in 0 into capital T, we end up getting 3/5, 0, and 4/5. And then here we have our normal vector, so then if we evaluate n of 0, that is, let's see, sine of 0 is 0, cosine of 0 is 1, and then we're multiplying it by -1, and then the last component is 0. So we're taking the cross product of these two vectors, and when you take the cross product of these two vectors, you end up getting 4/5, 0, and -3/5. So there is our answer for part B. All right, so part C says find the equation of the normal plane at 0, 3, 0. And again, I just want to reiterate, this is when t is equal to 0, and I've drawn a picture here. So this was that function that we thought of with the hang glider. So at t equals 0, they are at this location right here, and they're continuing to go up as time passes. Now, if you return to the previous page, looking at the graphic on the right, you see that the normal plane is the one that contains the normal vector and the binormal vector. So looking at our picture here, I haven't drawn the binormal vector on this yet, and because it's equal to the cross product of t and n, that means that our third vector is going to be orthogonal to both of these vectors. So let's draw that. So if I'm using the right-hand rule to think about the cross product, then my binormal vector is going to look something like that. So there's my binormal vector. And we want the equation of the plane that contains the unit normal vector and the binormal vector. So we've previously learned in the section on lines and planes how to construct the equation of a plane. So let's go there next. So let's remind ourselves, for the equation of a plane, we need a point on the plane and a vector that is orthogonal to the plane. So looking at the picture on the right, we can see that a vector that would be orthogonal to this plane would be capital T of 0, and we calculated that earlier, and that was 3/5, 0, 4/5. So that would be our orthogonal, or normally in the context of the plane, we've called it the normal vector, but in this case, I'm going to call it the orthogonal vector so as to not confuse us with capital N. And then I just need an ordered triple that lies on the plane. And because we're evaluating it for t equals 0, we can use this as our ordered triple. So let's remind ourselves what the equation of a plane is. It was a times x minus x naught plus b times y minus y naught plus c times z minus z naught. is equal to 0. And in this case, right here, that is x naught, y naught, z naught, which happens to be 0, 3, 0. And then this represents our orthogonal vector. And so this is A, this is B, and this is C. So let's put those things together now. We have 3/5 times x minus 0 plus 0 times y minus 3 plus 4/5 times z minus 0 is equal to 0. Let's clean this up. All right, so for part C, as a final answer, we get 3/5 x plus 4/5 z is equal to 0. That is the equation of our normal plane. Part D says the equation of the osculating plane at 0, 3, 0. So once again, if you look at the graphic on the previous page, you see that the osculating plane is the one that contains the tangent and the normal vector. So let's try to do that. So I rewrote the plane equation from earlier, and once again, the equation of the osculating plane is the plane that contains the tangent and the normal vector. So an orthogonal vector we can use is the binormal vector. And then again, we can just use a point on that plane, which is the same one we've been using, 0, 3, 0. So then putting this together, we would have 4/5 x minus 0 plus 0 times y minus 3 plus, I guess minus in this case, minus 3/5 times z minus 0 is equal to 0. And now if we simplify this, this ends up giving us 4/5 x minus 3/5 z is equal to 0. So there is our equation of the osculating plane. All right, part E says find the equation of the osculating circle at 0, 3, 0. I just wanted to pull up this graphic that was on the previous page to kind of see what the relationship is. And then let's see if I can try to graph the osculating circle on my picture that's on the right now. All right, so in the light green color, I've gone ahead and I've drawn my osculating circle. So let's go ahead and try to find the equation of that circle. Now, from earlier, we reminded ourselves the parametrization of a circle, but putting those two parametric equations together, we can come up with the vector equation for a circle that has center h, k and a radius of r, and that would be h plus r cosine of t and k plus r sine of t. So our goal is to come up with this here. And let's see. So we know the relationship that the radius is equal to 1 over the curvature, and we calculated the curvature earlier. We found that the curvature at t equals 0 was... Just kidding. I looked back at my notes and I thought we had calculated the curvature, but I guess not. So let's go ahead and do that now. So the curvature at t equals 0, we can calculate by evaluating t prime, or the magnitude of t prime of 0, divided by the magnitude of r prime of 0. Both of these magnitudes that we calculated earlier for the general t value, both of those magnitudes ended up being constants. So what do I mean by that? We found both the numerator and the denominator in previous parts of this question. And so if you go back to your notes, we found that the numerator, the magnitude of t prime, for all values of lowercase t was 3/5, and the magnitude of r prime, again for all values of t, because it ended up being a constant, was 5. And so that would also mean that the curvature at 0, which would make sense because if you are traveling along this path, even though you are going upwards, if your car started at that bottom point there, you wouldn't be changing your the rotation of your steering wheel. It would be the same. So it makes sense that the curvature for this helix is a constant value for any value of lowercase t. So that means that including at t equals 0, it's a constant. So 3/5 divided by 5 is 3/25. And again, our curvature for this helix should be the same number everywhere, because as you're driving up this really weird windy road, maybe you're in a parking structure. If you've ever been to the parking structure at the SeaTac airport, they kind of have these helical column things as you're driving up the parking structures. You'll notice that you're not really changing the orientation of your steering wheel. So the curvature is constant everywhere. And in this case, at 0, our curvature is 3/25. So now what I've drawn is a zoomed in version of our osculating circle, because right now at this stage what I'd like to do is I'd like to find the center of our osculating circle. And I erased the picture, but remember we saw that the normal vector looked something like this, and then the center of our osculating circle is here. So if I extend the normal vector by a scalar amount, that will get me to the center of my circle. All right, so now what I've drawn is a kind of zoomed in version. Also, in my original helical picture, my osculating circle wasn't big enough. So we can see here from these first two images that the normal vector, if we extend it by a certain amount, would go through the center of our osculating circle. And so we want to find the center of our osculating circle. So essentially, I'm trying to find this location right here, which is supposed to represent the center of our osculating circle. And the way that we can get that is, I know that a point on my circle is 0, 3, 0, which is right here. So I can start with 0, 3, 0, and then plus, we want to essentially add a scaled version of our normal vector. And we found the normal vector in general in part A, and that was equal to negative sine of t, negative cosine of t, and 0. And so if we want to find n of 0, that would be 0, negative 1, 0. So this blue vector right here, our normal vector at t equals 0 is 0, negative 1, 0. And I want to add that, or a scaled version of that, to my 0, 3, 0 vector. And how do I scale it? Well, I'm scaling it by the radius of my circle. So let's see. We found our radius to be 3/25. So if I take the reciprocal, or excuse me, we found the curvature to be 3/25. So the radius is going to be the reciprocal of that. And then I'm adding my normal vector that we found, which was 0, negative 1, 0 here. And so if we put this together, we can see that the center of our osculating circle, if we add those two vectors together, we end up with 0, negative 16 over 3, comma 0. All right, so I found the center of my oscillating circle. I wanted to go back and talk about a circle in 2 dimensions. Its vector valued function we said earlier was h plus r cosine of t, comma k plus r sine of t. And I want to break that up now into h comma k, which that represents the center of my circle. And then notice here in the way that I've broken it up, I could rewrite this as this vector really represents I, and this represents j. And the reason that we're using I and j is because they kind of represent our vectors that are along our x and y axis. But now, because of our oscillating circle, our x and y axis are not quite the same. And the other axis that we need to be using and thinking of is now our tangent vector. So these become our new, like, quote unquote x and y axis. And so back down here in our definition, this is also our center. So now the equation of our oscillating circle in 3 dimensions is going to work very similarly. So we have r of t is equal to, the center vector we just found was 0, negative 16 over 3, comma 0, plus the radius of our oscillating circle we found earlier, and that is the reciprocal of the curvature. So that's going to be 25 over 3 cosine of t. Now I need to multiply this by what we kind of view as our new x-axis, and that would be here, because you notice our x-axis is here and it's lined up. So we're going to use our t vector to kind of represent our new x-axis for our circle. And so I erased it, but we need here capital T of 0, which we found earlier to be 3/5, 0, and 4/5. So that's what I'm going to put here. And then continuing on with the pattern that we have above, we would have plus 25 over 3 times sine of t. And then our new y-axis, so to speak, that would be here, and we would be utilizing our n vector, our normal vector. We found that earlier was 0, negative 1, 0. And so this represents our vector equation of our oscillating circle in 3D. Let's clean this up and put it into a single vector equation, or a single vector. So let's add the x components first. Here we have 0. If I distribute this term into the first component, that would also be 0. And then that means that I just need to multiply 25 thirds cosine t times 3/5. That is going to be 5 cosine of t. And then let's add the next component. So I'm going to have negative 16 over 3 plus 0, and then minus 25 thirds sine of t. And then let's add the z components now. So I have 0. I need to multiply 4/5 times 25 thirds cosine of t, and then the last part is 0. So let's see, 25 divided by 5 is 5. 5 times 4 is 20. So that's going to be 20 over 3 cosine of t. And here is our final answer for the equation of the oscillating circle. All right, so here I just wanted to show you, in the red, I've graphed the helix that we were looking at, and then here I've graphed the equation of our oscillating circle. So let me minimize that. And then you can see here's our helix and then our osculating circle. It's kind of angled, so I wanted to provide this three-dimensional view so that you have a better idea. There is our osculating circle. And here's another example. We have this orange space curve, and then in blue, we have the osculating circle as it travels around. And notice that its orientation changes as well as the radius of it, because remember, the radius is related to the curvature of our curve. So it's changing radius as it moves around. So that's pretty cool. And the last thing that I wanted to illustrate here is here again we have a space curve, and then the red, green, and blue vectors represent the tangent, normal, and binormal vectors. And so notice that these, the normal plane, the osculating plane, change as you move along this 3D space curve. All right, so that concludes this video on arc length and curvature. Thanks for watching.